So we'll start on the first exercise problem, which is to verify that the ordered pair AB equals the ordered pair CD if and only if A equals C and B equals D. Now, there is one very easy direction in this proof, which is the right to left direction, assuming that A equals C and B equals D. Then we can go ahead, and if we want to be very sort of tedious about this proof, I mean, if we didn't, we could just say that we could do substitution in that case, but if we want to be more tedious, then we could say that the ordered pair is equal to this set, right? So ordered pair AB equals this, and now we could argue that the set A is equal to the set C by the extensionality of sets, and therefore it doesn't matter what the presentation is, A or C. All that matters is equality of the contents of the set, and so we get to do replacement there, and then we get to do replacement yet again here, which just is the ordered pair C. So that's fairly trivial. The other direction is harder. A bit. It's not exactly a hard concept, but it just requires chasing down a lot of cases, but here it is. Suppose that the two ordered pairs are equal, and that means these sets are equal. Well, by equality of sets, it means that this element must be located somewhere in this set, which means that the set A is either equal to the set C or it is equal to the set CD. There are no other options, so we branch into two cases. If the set A is equal to the set C, that seems pretty good. We get what we know we want, which is that everything in this set must be in that set, therefore A must be equal to C. There are no other options. So we have that much. Now we need to show that B equals D. How are we going to do it? Well, we look in the other direction and say that the set CD must be located in the pair AB, which is this up here. That means that the set CD is either equal to the set A, not as ridiculous as it might sound at first, because after all, we do not know whether C and D are the same element. If they are, then these really could wind up being the same set. Right, we have to entertain the possibility that CD is equal to A, or that CD is equal to AB. So again, branch into two cases. In the first case, CD equal to A, then that means that everything in this set must be in that set, therefore C must be in here, so C is equal to A. We already knew that. D must also be equal to A, and now we have the equality of these three elements. In that case, if you just kind of spell out and reduce in representation this pair CD, it'll reduce down to this. We've seen that in an earlier video, basically. Well, in that case, since that's what the pair is, and the pair, or the set AB must be located, right? Again, going off of the fact that everything in this set must be located in this set. AB must be located in this set, but we have just shown that this set is equal to the set of the singleton C, so AB must be equal to the singleton C, and so now B must be located in here, and therefore B is equal to C, and therefore since B is equal to C and C is equal to D, B is equal to D, and that's exactly the result that we wanted. Okay, a lot of work for a simple result, but, you know, I'll kind of end here. The rest of the proof goes similarly. You can see my writing of the rest of the proof here, but, you know, the logic of the argument is pretty much just as what you've been seeing so far, so you should be able to read the rest.